Okay, let us continue to the Jacobian. By summarizing about this one, this one shows the essential of Jacobian. Actually, if we had this kind of transformation matrix, yes, this one is S1 to I minus 1. It means the homogeneous transformation matrix from the space frame to I minus 1's joint. So by using the other joint of this transformation matrix, we can change some screw axis to the other screw axis. So actually, JSI itself is a kind of screw axis, and this one is about the transformation about transform of SI. Actually, SI equal to the I's screw axis based on the fixed frame in a zero position. So this means zero position screw axis based on the fixed frame. And this one is transformed using this T matrix. So that becomes JSI, the Jacobian column of I's Jacobian column. So let's practice about this. And this one is kind of RRP manipulator. We call this one, sometimes we call this one scalar robot. And there is rotation axis, three rotation axis, and one translational axis. Okay. In this example, we have to find Jacobian matrix. Jacobian matrix like this. So to find this one, only need to do is to find screw axis. And that is very similar to the forward kinematics. So in the rotation axis, about the rotating screw axis can be found using in a space based on the space frame, and the space frame is here, and the rotation axis theta 1, theta 2, theta 3 is rotating with the g axis of the space frame. So it becomes 0, 0, 0, 1, 0, 0, 1, 0, 0, 1. And there is a translational axis. In this case, rotating screw axis become 0, V become 0, 0, 1, because it is moving Z axis. So 0, 0, 0, 0, 0, 1. And then there is a little bit difference to find about this one. To find V, we have to multiply Q cross product omega. In case of omega is given like this, and about the Q, Q have to find based on this rule. Actually, JSI is the screw axis. So screw axis means this one. The screw axis we only found in the zero configuration in the forward kinematics, but in case of Jacobian, we have to find some variable theta about the variable theta. So there is some movement depend on the variable theta. So in case of Q, it is function of theta. So Q2, let's find Q1. Actually, Q1 is there is some point on this axis. So it becomes 0, 0, 0. In case of Q2, it located along this axis. And this one is rotated by theta 1 and theta 2. So this figure itself shows the some kind of movement depend on the theta 1, theta 2. So if we choose Q2 as this one, this Q2 point can be calculated by L1 cosine 1 theta, L1 cosine theta 1 and L1 sine theta 1. So actually, if the x-axis is like this and y-axis like that, then we can calculate this point using this equation. In case of Q3, also we can calculate like that. So using this Q2 and Q3, we can calculate V. So using this information, we can construct JS1. JS1 becomes 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, and JS2, 0, 0, 1, L1 sine theta 1 minus L1 cosine 1 and 0, and like this and like this. So this one itself, this table itself, becomes Jacobian. So even though we found the equation is seems very complex, but actually the Jacobian can be found very, very easily. Let us find the other example in here. Okay, let's continue to the example 5.3. In case of 5.3, there is rotational axis and there is prismatic joint. So in case of theta 1, this one is rotational axis along the z-axis. So it becomes simply 0, 0, 1. In case of second joint, before we continue to theta 2, we have to find some Q1. Q1 is here. Q1 is selected along this axis, and we select Q1, and Q1 is 0, 0, L1. And by multiplying these two things, okay, by multiplying these two things, it becomes like this. So it becomes 0, 0, 0. And then Q2, in case of this theta 2 axis, actually in the zero configuration, it becomes -1, 0, 0. But in case of theta 2, it depends on the theta 1. So if the theta 1 is rotating, the theta 2 axis is changed, depend on the theta 1. So this omega 2 should be like some kind of C1 minus CS1, 0. And in case of Q2, we can choose this same one, 0, 0, L1. And then the S2, VS2 becomes LS1, L minus L1, C1, 0. So in case of theta 3, this one is prismatic joint, so translational movement. So in case of omega, it becomes 0, 0, 0. And then Q becomes Q is not necessary. Q is not necessary. We can just we should find the V using theta 3. Actually, theta 3 is also depend on the theta 1 and theta 2. So in the zero configuration, the direction is y direction, same with the y direction. So using 0, 1, 0, and this direction vector is transformed based on the minus theta 2 along space frame axis. So it multiply the absolute transformation here. And then we also transform theta 1 using Z, space frame Z and theta 1. So this multiplication is pre-multiplication. So it means absolute transformation based on this S frame. So by using these two rotational matrix, we can find V like this. So this becomes minus S1, C1, C2, and C1, C2, minus S2. And then about the fourth joint, in 4, 5, 6, there is one point, there is one intersection point of these three axes is coincide. So this, let's find this Q omega QW point. The QW point is calculated using this equation. So you can understand about this one. Yeah, I will ignore to write down here. So this one is QW, and omega 4 is the calculation is a little bit a little bit long. So I will briefly explain about this one. The theta 4 is rotating z-axis. So based on the 0, 0, 1, it rotates using actually the rotation axis. The only important thing is about the direction. So we only multiply the rotation matrix. So it depends on the rotation of theta 1 and theta 2. So we multiply this one on the 0, 0, 1. And about the fifth rotation, this rotation is minus 1, 0, 0, minus x-axis rotation. So minus 1, 0, 0, multiplying this one. And in case of theta 5, it depends on the theta 4. So this one is also multiplied. And the omega become like this, and omega 6 become like this. And in case of the V becomes more complex because it is cross multiply with Q omega. So I will ignore, I will skip to write down here, but the calculation process is can be checked using this equation. So actually we learned about the space Jacobian, but in case of Jacobian, okay, the example 5.3 can be calculated using like that. And let's continue to the body Jacobian. About the body Jacobian, actually in the space form POE, we use this kind of calculation, T dot T inverse. How about body POE, body form of POE? Body form of POE, in case of body twist, it becomes T inverse T dot. So actually, you might know we have to find this kind of form. So let's have some time derivative of this body form POE. In that case, we can calculate the first element is from the nth axis, and then n-1 axis, and and then we can get the similar format like that. So in this case, we multiply T inverse in the front, then we can erase, it can erase this one. So in the first element, we can get this element, and then etc. So actually this small SC3 matrix form of this equation can be converted to the 6-vector form using adjoint. So we can get this equation. The velocity, the twist, body twist can be calculated using this kind of calculation. In here, we have very most simple format on the nth axis and most complex format on the first axis, because we are thinking about the Jacobian based on the body end effector. So the end effector is closest to the nth joint. So this one is most simple, and this one becomes most complex. So similarly, with the space Jacobian, the body Jacobian becomes like that. And the meaning of the JBI is almost the same with the space Jacobian, but the different thing is based on the end effector frame. So the definition of JBI is screw axis. It means also screw axis of ice joint when the theta is applied based on the end effector frame. So actually, the two concepts is almost similar and almost the same, but the base frame is different. So, okay, let's continue to the relationship between space and body Jacobian. This equation is the small SC3 form of space twist and body twist. And this one is the relationship of space twist and body twist in a 6-vector form. In this case, we use the Jacobian, adjoint. And in this class, we learned about the Jacobian, space Jacobian, and body Jacobian. Okay, in here, this one is equal to this one. So we can write down like this. And if we multiply adjoint TBS like that, and then these two things is erased, and the body twist is remained, and this one. And in the upper equation, this one was same with this one. So we can get this equation. So by erasing theta, then we can get this one and this one. So the translation of Jacobian can be done using adjoint. So space Jacobian can be transformed using adjoint TBS, so like that. And body Jacobian can be transformed using adjoint TSB like this. So this one is almost the same format with twist. So in here, the body twist can be transformed space twist like this, and space twist can be transformed body twist like that. So actually, these two format is the same, because the Jacobian column itself expressing the screw axis. So this kind of things can be happen. So let's continue to the singularity. Singularity means when in the equational level, we can think the degree of freedom is dismissed. In the 6 DOF freedom robot arm, if the arm is stretched like that or is folded like that, then in that case, the degree of freedom is reduced. So in this case, we call this one as singularity. So the singularity is related to the Jacobian. So Jacobian is some kind of matrix depend on the degree of freedom. So if the robot is 6 degree of freedom, the space Jacobian becomes 6 by 6 matrix, the function of theta. But when in some theta, if the length of this Jacobian, space Jacobian is less than 6, then in the case, the singularity happens. So we should be careful about that. The property of singularity is the body, if the length of body Jacobian and space Jacobian is always same, and the singularity is not depend on the fixed frame or end effector frame. And let's learn about manipulability. Manipulability is how much the singularity will be happen. So if theta is like, there is theta 1, theta 2, theta 3 velocity, and the size of theta 1 dot, theta 2 dot, theta 3 dot is equal to 1, then means unit velocity. If we multiply Jacobian with the theta dot, we can get the task space velocity. So it becomes V1, V2, V3. So depending on the Jacobian, the sphere shape of the size of theta 1, theta 2 dot, theta 3 dot become some kind of ellipsoidal shape, depending on the J. So this J can be this kind of the shape of this ellipsoid can be calculated using J multiply J transpose. So let's define this one is A. So the eigenvalue of A becomes the size of the size of ellipsoid, and the eigenvector of A becomes the direction of this axis. So using J transpose, J multiply J transpose equal A, using this A, we can get the manipulability of the manipulator. So we define here the condition number mu. Mu is dependent on the A, and by using A matrix, we can calculate lambda max and lambda min. Lambda max is the largest eigenvalue of A matrix, and lambda min is smallest eigenvalue of matrix A. So the ratio of these two things is greater than 1. Actually, when the mu number is close to the 1, this ellipsoid is close to the sphere. So if the mu number is equal 1, this ellipsoid become sphere. But when some axis is close to the 0, in the case the singularity is happen. So it is better to make this ellipsoid to the sphere. In the case in all direction, the velocity is well generated. So the manipulability is good. But in case of very narrow, if there is some narrow plane, then in the case some velocity direction is not well controlled. So in the case, there is possibility to happen, high possibility of singularity. So condition number, it is better to make the condition number equal 1. So until now, we studied about the Jacobian and singularity and manipulability. Actually, the singularity and manipulability is very briefly explained. So it's not that important, but in some case it is important, but it generally is not important. So the important thing is Jacobian. So I want you to practice more about the Jacobian. So I will give some practice problem on the LMS system. So thank you. The class is over.